And our check would be the same as it is here. Again, even though we used a different method, the method of substitution rather than graphing, if our solution was 6-1 and these were our two original equations, our check would be the same. And as we've seen, indeed it does check. So let's talk momentarily about the two methods we've used, and then it looks like we'll have some time. We'll go on and look at a third method, which is called solving by addition of equations, and we'll proceed with that, which will lead right into Lesson 11, which will take up some more complex types of equations. What we've done so far is looking at the solution to two equations to find the intersection point. The first method was graphing. Get the equations in some form, probably y equals mx plus b, that you can graph the two equations on the same set of axes, and where the two lines cross, that's your solution. Find the x and y, go back, plug the x and y into the original equations, and check that that solution is indeed working for both solutions. The second method we used was by substitution. We either had one equation that had x equals a function of y, or possibly y equals a function of x. If we didn't have that, we took one of the equations and solved it for x. So we got x equals a function of y, or we solved it for y. We got y equals a function of x. And then we substituted, so we got an equation with only one variable. We know how to solve those. We solved. We used the other equation to find the value of the second letter, and then we went back and checked in the two original equations. Quite frankly, those work well, but they're not the easiest methods to use. As we saw with the graphing, we could wind up with some fractional situations. In substitution, we have a problem. Sometimes it's not very easy to take either of the equations and get x as a function of y or y as a function of x without running into problems with fractions. And again, you may enjoy fractions, I don't. Historically, many of my students have great problems with solving equations that have fractional numbers. If we can avoid that, that sounds very good. And the way to avoid that is by looking at adding equations. Now you say, well, what do you mean adding equations? Well, if we have two equations, let's take an example. Let's go to the board again here. And let's take an equation like 2x plus 3y equals 8. And how about 5x minus 2y equals 1? If I added those two equations up, what would it do? Would it create another equation? Can you prove that? If you said the answer was yes or no. And the answer, by the way, is yes. And the way to prove it is, hey, 2x plus 3y, that equals 8. If I add 5x minus 2y to this, it's no different than adding 1 to the 8. I'm adding equals and equals. What I get is an equation. In this case, remembering from Algebra 1, we can only add x's and x's. 2x plus 5x is 7x. Positive 3y and a negative 2y is plus y. And 8 plus 1 is 9. And you might say to us right now, well, what good have we done? We haven't done any good in terms of solution. I was doing this to show you how we could add equations. Our goal in adding equations, you see, is to eliminate one of the letters. We can do that by eliminating the x's. For example, if this had been 2x and this had been negative 2x, when we added those equations up, the x's would go away. If this had been a positive 3y and a negative 3y, the y's would have gone away. So we either eliminate the x's or eliminate the y's. How would we do that here? We'll leave that for Lesson 11. But right now, we want to look at equations that are in such form that if we do add the two equations up, we can immediately eliminate one of the letters and go ahead and solve. Because remember, once we get down to an equation with only one letter in it, we know how to solve those. So let's take a look at the first visual in this problem. And the first visual gives us the two equations. 2x minus 3y equals negative 13, and 5x plus 3y equals negative 1. Notice it would not be very interesting to graph these two equations, because you get it in slope-intercept form. You would have a slope of 2/3, which is and plus a y-intercept of 13/3, which is not a very interesting y-intercept to plot. That's for the first graph. And the second line would have a slope of -5/3 and a y-intercept of -1/3. We could use substitution, but again, in solving either of these equations for x or y, we'd wind up with fractional values. And it really would be a problem working with those. But notice something very, very nice. In the first equation, the one on top, we have a -3y. In the bottom equation, we have a +3y. If we should add those two equations up, the y's would go bye-bye, as we say. They would disappear. They would cancel each other out because they have the same number with opposite signs. And indeed, that's exactly what we do in the next visual. We add the two equations up. 2x plus 5x is 7x. The -3y and the +3y is 0. And -13 and -1 is -14. Once we have an equation with only one variable in it, we have no problem solving it. And of course here we simply divide by 7 and x equals -2. Are we done? Absolutely not. Remember, our solution has to have both an x and a y. So what do? We go back to one of the original equations. Let's look at the next visual. We can see I've selected to use 2x minus 3y equals -13. It doesn't make a difference which one you choose. We plug in the x of -2. So 2 times -2 minus 3y equals -13. And the rest of that lays out the solution. Again, we're back to one equation, one letter, in this case y. We can solve it. We add 4 to both sides. We get -3y equals -9. We divide by -3, y equals 3. And thus the last item in that visual is the solution, the ordered pair, -2, 3. Again, this means that for our two equations, 2x minus 3y equals -13, and 5x plus 3y equals -1, the only value of x and y that's common to both equations, the intersection point, is when x is -2 and y is 3. Now, we still need to check this, don't we? So let's look at the last visual in this set. And what we've done here is we've simply replaced the x and the y in the second equation, 5x plus 3y equals -1, with -2 and 3. The x is -2, the y is 3. We get -10 plus 9 equals -1. And that, of course, is correct. Why do we only check in one equation? Why didn't we check in the first equation, the 2x minus 3y equals -13? Because you'll remember, that's the equation I used to solve for y when we knew x. If you wanted to check in that equation, that's very fine. You can do it. But basically, you must check in the equation that you didn't use once you found the one letter. Could we have solved these equations by eliminating the y's? Well, obviously not. We did eliminate the y's. Could we have solved this equation, system of equations, by eliminating the x's? And the answer is not, as we know right now, because as we saw, 2x plus 5x is 7x. It doesn't eliminate the x. The next thing we're going to do in the next lesson is to see if for some strange reason you had said, gee whiz, I don't want to eliminate the y's, I want to eliminate the x's. Or if the two equations were not of the type where you had an x in one that was a +4 and the x in the other was a -4, and you couldn't eliminate by adding. For example, if we go back to the board here, remember this. What if we were faced with this particular set of equations? We certainly could not accomplish elimination by adding. We wouldn't want to get involved with graphing because of fractions. The same thing with substitution. And we'll talk about this next time. But right now, we do have 3 methods that are quite valid. We have the method of graphing, which is very, very good as long as you can easily graph the two lines. We have the method of substitution, which is an excellent way to work the solution if one of the two equations can be put in y as a function of x form or x as a function of y form. And then we have the addition method, which is simply very useful and exceptionally easy if either the two x's or the two y's have the same coefficient with opposite signs. As we saw here, we had the y's. One was negative 3y, the other was positive 3y. But ultimately, everything we've done in this lesson was to enable us to solve a system of two equations. Just as Malthus wanted to know where the supply and demand for food, those two lines would cross. In what year would the food and the demand for food and the supply of food be the same? Just as the business person running a company wants to know his or her break-even point, where revenue, the money coming in, would be the same as the cost or expense, the money he or she is expending. In those cases, we are dealing with systems of equations. Like I say, in the next lesson, we're going to deal with more complex equations, like the one we had on the board, and find a method that will work in every single case. And eventually, we're going to jump to a higher level. We're going to find out how we can solve systems of three equations with three letters. But that's for a later time. We'll see you in Lesson 11.